Hello, everyone, and welcome to my talk on RDMA replicated data types. My name is Farzin, and my collaborators are Jawad and Professor Mohsen Lassani from University of California, Riverside. Distributed computing is an integral part of many systems in finance, control systems, and distributed databases. And data replication is a means to performance, reliability, and availability of such systems. At the core of many replication protocol is a consensus mechanism that ensures total order of operations among replicas, which essentially provides strong guarantees such as sequential consistency that simplifies reasoning about the correctness of applications. From the long list of replication protocols, hardware-accelerated systems have gained recent attention because of their impressive performance. A prominent solution, RDMA, marks the advent of a new model in which nodes in distributed system can directly perform read or write operations without CPU involvement. This new model provides blazing fast communication, and that's why many systems used RDMA to implement state machine replication that are orders of magnitude faster than traditional message passing. However, these systems rely on blanket strong consistency. Although these strong models provide favorable properties, there is a caveat. Consensus is known to be expensive, and systems that rely on strong consistency are slow. Practitioners soon realize that such systems do not provide responsiveness and availability, therefore they opted for more relaxed notions of consistency that forego the total order and perform much better and faster. But these relaxed notions suffer from weaker guarantees, therefore make the reasoning about the correctness of applications harder. Several solutions have come up with hybrid consistency models in which operations execute either under strong consistency or weaker notions based on their semantics. These systems are more efficient and provide better responsiveness while providing enough guarantees for the application. However, these are all dedicated to message passing model. The focus of our work is to bring hybrid replication to RDMA world. We present the first hybrid replicated data types for the RDMA network model. At the core of our hybrid model is well coordination, which is a sufficient condition for integrity and convergence of replicated data types. But to understand well coordination, we have to first look at the notions of conflict and dependency. Throughout the presentation, I'm going to use a simple bank account object with a balance that represents the state, and I'm going to use an integer which represents the balance and a non-negative integrity property. This object also consists of three methods: deposit, withdraw, and balance. Let's look at an example of conflict. Assume two replicas are starting from the same balance 10. The first replica executes a withdraw of 5, which results in a balance of 5. We say that this call is permissible in state 10 because it results in a state that preserves the integrity. Meanwhile, another replica executes another withdraw concurrently that results in a state of 4. The first withdraw will be delivered to the second replica after the first withdraw, which results in a negative balance and violation of integrity. We say that this withdraw is not permissible in state 4. Therefore, we call two withdraws are conflicting. Finally, we represent the conflict graph, conflict relation as a undirected graph where each edge represents the conflict relation between pairs of operations. Let's move to dependency. The withdraw in the first replica is only permissible because of its preceding deposit call, and it becomes impermissible and violates the integrity if it's moved to the left of the deposit. Therefore, we say that a withdraw depends on the deposits. Similarly, we represent the dependency relation with a directed graph where each edge represents the dependency from the source to the destination. Now we can see the conditions of a well-coordinated execution. First, all the calls must be locally permissible in their originating node. Second, all the conflicting calls must be synchronized to have the same total order across replicas. And finally, the causal relationship between dependent pairs of operations must be satisfied. We say that such replicated execution preserves integrity and convergence. Let's look at an example. Our goal here is to replicate our bank account object on 3 nodes in RDMA network. To do that, we have to replicate balance, which is an integer, on these 3 nodes. We also allocate a piece of memory for the RDMA controller in each node. But to avoid synchronization, we divide this piece of memory between all the nodes, and we use a single writer design to do that. So each node gets its piece of memory in all the nodes. We categorize methods of our object into 3 classes of irreducible, conflict-free, conflicting, and reducible. Each class has its own coordination mechanism, and I will explain them in detail in turns. Let's start with a conflict-free method such as deposit. Assume that the client issues a deposit call to the first node. The first node starts replicating the call by writing it to the corresponding log of other nodes. And meanwhile, this call is executed on the first node, and the state is updated accordingly. Assume another client issues another deposit call, but this time to the third node. This node also replicates the call and writes it to the log of other nodes and updates its own state. Until this point, nothing has been executed on the second node. To process the calls in the buffer of all the nodes, a thread periodically goes over the calls in the log, executes them, and applies them to the state. This happens at every node, of course. And after all the calls are processed, we see that the state of all the nodes converge to the same state. Let's move to the second category, the conflicting. As an example, a withdraw call. Based on well coordination, all the conflicting calls must be synchronized. To find out which calls need to be synchronized with each other, we have to use a notion called a synchronization group. Synchronization groups are strongly connected components of our conflict graph. As an example, in our bank account example, the conflict graph consists of only a single synchronization log. To do fine-grained synchronization, we use and assign a synchronization log per synchronization group. Therefore, we have a single synchronization log in our example. And the reason is that the calls in our synchronization groups get ordered with only a single leader that represents that synchronization group. Back to our example, we store and allocate a piece of memory for the synchronization log in our nodes, and assume that the first node in green is the leader for this synchronization group. Assume 2 client issues 2 withdraw calls concurrently. The calls to withdraw are handled and ordered by the leader. Therefore, the leader first executes the withdraw 15 and makes the state 5. However, since the other withdraw 10 is not permissible, the call is rejected and is not executed. If we assume there were no dependencies, the call would be simply replicated to other nodes by the leader. But the question is, how do we handle dependencies? So to track dependencies, we have to store the number of applied calls in a map in which each keys represent the node identifier and the values store the number of applied calls. This map is pair dependency relation, so we might have multiple of such maps. To replicate the call, the dependency is sent along with the call, and a call can only be applied if the local map is greater or equal than the dependencies. Let's for a second assume that the deposit in the second node is not yet processed by this node. So the map shows 001. The leader replicates the withdraw along with its dependencies to the synchronization log of others. However, since the Since the second node is not updated with its dependencies, the call is not executed and it remains in the log to be checked at a later time. In contrast, the third node is up to date with its dependencies, so the call is executed immediately and applied to the local state. We saw an example of conflict-free and conflicting operations. Let's see what reducible methods are. But before that, we have to understand what summarization is. As an example, a deposit 10 operation and a deposit 5 can be summarized as a single deposit of 15. We say that 2 calls are summarizable if the composition of 2 can be represented as a single call. We also say a method is reducible if the calls of that method are summarizable, conflict-free, and dependence-free. We observe that these reducible calls are even remarkable. These can be replicated even more efficiently without needing to process the calls in the receiver side. Let's look at an example. We saw that deposits are reducible. So instead of having a log at each node, we can simply store a single memory location for deposits. And when a call wants to replicate the deposit, it simply summarizes it with its own local summary and writes the summary locally to ourselves and writes it to others. We see that others just got updated without even needing to process the deposit call. We have presented the abstract semantics of well-coordinated replicated data types that present the coordination conditions for these data types. We saw how these RDMA well-coordinated replicated data types are implemented in practice, and we have a concrete operational semantics for that in the paper. We have formally proved that these RDMA WRDTs refines the abstract semantics. Therefore, any RDMA WRDT preserve integrity and convergence. Let's move to experimental results. We have compared our throughput and response time of our system with message passing and sequentially consistent new system with 3 conflict-free methods. In our response time results, we see that our system is significantly more responsive than the other 2 systems in different applications with different workloads. Also, our throughput results show that our system exhibits more throughput and scalability across the board with respect to the other systems. Next, our experiment with conflicting operations and conflicting methods show that our system can significantly provide better throughput, and that's mainly because of our fine-grained synchronization mechanism that increases parallelism among the nodes. And finally, let's look at our fault tolerance result. To be able to handle crash failures, we had to come up with a new broadcast mechanism in RDMA networks. We have implemented this reliable broadcast abstraction, and I encourage you to look at this in the paper. The crash failure results show that, for example, in follower failure scenario, our throughput gets affected, but not by much compared to the leader failure scenario. Also, the response time results show that methods do not get affected when the follower crashes. And also, finally, the conflict-free operations do not get affected even when the leader crashes. In conclusion, I introduced well coordination and a glimpse of how these replicated data types work. We saw RDMA well-coordinated replicated data types, and we have presented concrete semantics for them that categorizes methods into 3 categories and defines separate coordination condition for each. And we have formally proved that these RDMA WRDTs converge and preserve the integrity. Thank you so much.
Let's thank Farzin.
Thank you for a great talk. I have a question about, I saw you use InfiniBand to connect the servers. So I assume that they need to be like in the same data center or in the same rack of servers. So I'm wondering if your technique can be applied to like replication across different data centers or in different locations.
Right, that's a very good question. So basically, our RDMA implementation relies on the fact that the nodes have to be connected using RDMA protocol. And that's normally provided in only a single data server. But the well coordination in general can be applied to geo-replicated databases, and it can benefit from any sort of network. But RDMA ones, yes, they have to be in the same network to be able to handle RDMA communication.
I have a few questions, but I'll limit myself to just asking about the summarization. The summarization routine replaces multiple queries with a single, or multiple updates with a single one that summarizes it. How are you able to I'll just take my mask off.
Sorry.
This will be much easier. Sorry, this mask, anyway. The summarization operation replaces a set of operations with a single one. How are you able to determine that the receiver of the summarization operation has not received a partial log of the operations it is summarizing?
Right. So we have these summarization groups, and we have formally defined them in our paper. So for each set of summarization methods, we have a summarization group. And we make sure that we respect whatever we have summarized in that memory location, so we don't basically do operations multiple times. We make sure that the state is well maintained with these summarization groups.
A quick follow-up. Summarization is normally used as a compression technique to deal with less operations. It sounds like your summarization groups will need to keep all the operations that are being summarized around. So what is the concrete benefit that summarization gets you?
Not necessarily, because as you summarize multiple calls into a single call, you don't need to keep them anymore. It's just represented as a single call in your local summarization group, memory location, and in other remote locations.
Okay, so I guess let's thank Farzin and continue with our next speaker. So.